See, electrochemistry is a branch of chemistry which deals with the interconversion of electrical energy into chemical energy and chemical energy into electrical energy. See, nowadays we are using batteries in the vehicles. Vehicle battery. In vehicle battery, what happens? Chemical energy will convert it to electrical energy. And in day-to-day life, this electrochemistry concept is used in different areas. For example, electroplating. We can plate iron rod with gold layer. That depends on the electrochemistry, based on the concept of electrochemistry only, right? And in the purification of metals also, in the earth crust, some impure metals will be extracted. That will be purified by electrochemistry concept only. Clear? Mainly batteries. Batteries works based on the redox reactions. Will be explained by electrochemistry. Clear? Right. Terms used in the electrochemistry terminology. So I'm not giving definition, you can go through the PDF. It is a branch of chemistry which deals with the interconversion of chemical energy to electrical energy and vice versa. See the terminology. Surabhi, Aisha. Conductor. The substance which allows passage of current through it is called as conductor. Best example, iron. Metals are good conductors. Metals allows current through them, so they are called as conductors. Insulator means which do not allow. Simple definition, right? Conductor, substance which allows passage of current. Through it is called as conductor. Conductor is two types. Metallic conductor. Another name for metallic conductor is electronic conductor. Which of the following is electronic conductor? Metallic or electronic conductor. Second one is electrolytic conductor. Electrolytic conductor. Metallic conductor. Metallic conductor nothing but a simple metal. Metals are called as metallic conductors. All metals. Say one example for metal. Iron, copper, silver. Metallic conductor. What is electrolytic conductor? Mariha, listen. Electrolytic conductor. The substance which allows current in its fused state or in its solution state. Fused or molten. See, fused and molten both are same. Molten. Solution state. Fused or molten. What is the meaning of fused or molten? Take a salt, one salt. Take a salt in a bowl and heat it without adding any water. At particular temperature it will melt, converted into liquid. That is called as fused state. If we heat the salt directly without adding water, at particular temperature it will melt. That melt or liquid form is called as fused state or molten state. Clear? You tell me, in that fused state or molten state, is there any water? No. Water is not present, right? So few ions only present, a limited numbers, one cation, one anion, based on the salt. If you take mixed salt, some number increases, but water is not present. In fused or molten state, water is not present. Clear? And solution state. Solution state means take salt in water. Okay, dissolve salt in water, then you will get solution. So salt, electrolytic conductor means salt. Salt is example of electrolytic conductor. Salt conducts current in its molten state. Means melt salt by heating. Clear? Not solid salt. Solid NaCl is bad conductor of electricity. Why? Because free ions are not present. Free ions are not present. We have to melt. Okay, that melt salt is nothing but a fused state. Best example for electrolytic conductor is salt. Substance which allows passage of current in its molten state or in its solution state. What is the example? Sodium chloride salt. Sodium chloride. Right? Let us see the differences between metallic conductor and electrolytic conductor. In metallic conductors, these points may come. Sorry. What is responsible for electrical conductivity in metallic conductor? Let us take one metal. Differences. These are differences. Consider these are electrons. Free electrons are responsible for electrical conductivity of metals. This is a metal rod, iron rod. Can we see electrons inside it? We cannot see, but electrons will move. Clear, in the metal crystal. So what is responsible for electrical conductivity in metals, metallic conductors? Free electrons. Free electrons are responsible. If we take iron rod, inside free electrons are present. That's why they carry current. Clear? What is responsible for electrical conductivity of metallic conductors or electronic conductors? Free electrons. In electrolytic conductor, what is responsible for electrical conductivity? Free ions. Free ions are responsible for electrical conductivity. Main difference between electronic conductor and electrolytic conductor. Free electrons and free ions. Metallic and electrolytic. Free electrons are responsible for electrical conductivity. Free electrons are responsible for electrical conductivity. Here, free ions are responsible for electrical conductivity. What happens if we increase the temperature? That is very important. What happens to metallic conductance upon increasing the temperature? What happens to electrolytic conductance upon increasing the temperature? See, take a solution, sodium chloride solution. Heat it. What happens? If any undissociated sodium chloride particle is present in it, undergo dissociation. If you heat solution, if any sodium chloride particle is present in undissociated form, it undergo dissociation, means number of ions increases. So conductance increases. In case of electrolytic conductance, if you increase the temperature, conductance increases. Upon increasing temperature, conductance increases. This one. What happens to metallic conductance upon increasing the temperature? See, for metals, for metals, when we increase the temperature, when we heat this metal rod, iron rod, its resistance increases. If resistance increases, then conductance decreases. So metallic conductance decreases upon increasing the temperature due to increase in the resistance. ఏమైందమ్మా? ఆగిపోయిందేమని నేను అనుకున్నాను. Conductance decreases upon increasing temperature due to increase in the resistance. Conductance and temperature. Can I draw like this for silver, for copper, for iron? Can I draw? At low temperature, conductivity is very high. In this direction, temperature increases or not? In this direction, temperature increases. So as we increase the temperature, conductance decreases. Which conductance? Metallic conductance. Conductance. For example, this graph is for, see, conductance, a generalization. Conductance, this is metallic conductance. Metallic conductance decreases due to increase in the resistance. And this line, which conductance? Electrolytic conductance. And one exceptional case is there. This is general idea. One exceptional cases is there. You know, silicon and germanium. What is common name for silicon and germanium? Semiconductors. For silicon and germanium also we can observe increase in the conductance upon increase in the temperature. Silicon and germanium. Semiconductors, exceptional cases. Semiconductors means their conductance value is intermediate between conductors and insulators. Generally metals conductance decreases, like iron, copper. We know electrolytic conductance concept, but for silicon and germanium, graph will be like this. Semiconductors, these are semiconductors. వైష్ణవి 4K కదా క్లాసు, అందుకని రికార్డ్ పెట్టాను మీకోసం. రికార్డ్ పెట్టానమ్మా, మిస్ అయితే వింటారని. ఓకే, క్లియర్ ఆల్ ఆఫ్ యూ. Surabhi will answer this question. Electronic conductor. Silver electronic conductor. Remaining are electrolytic conductors, salts. Even see HCl also, NaOH also considered as electrolytic only, because their solutions conduct electricity. We have to add that also in the electrolytic category. I said salts only, but we can include HCl also. What happens when we dissolve HCl in water? HCl is a good conductor in water. If you drop HCl in water, it undergo dissociation, produce H plus and Cl minus. It is a good conductor. Now you tell me, when we dissolve or when we pour HCl in benzene, is it good conductor? Benzene is a non-polar solvent. HCl do not undergo dissociation in benzene, so it is not a good conductor. HCl is a good conductor in water, in the presence of water. Aqueous HCl is a good conductor. But when you dissolve HCl in benzene, then HCl do not conduct current because it do not undergo dissociation. Write one note, Bhakti. HCl is a good conductor in water, but not in non-polar solvents. Benzene, CCl4, non-polar solvents. Now answer this question. Seniors unnaru kada andaru ikkada. Mixed conductor. How to classify conductors? Electrolytic. Next, metallic. Mixed conductor means both. How both is possible? Conductors are two types: metallic conductor, electrolytic conductor. Metallic conductance means conductance due to free electrons. Electrolytic conductance means free ions. Mixed conductors. Mixed conductors means mixed conductor is having the properties of metallic conductor and electrolytic conductor. Sodium in liquid ammonia. The solution of sodium in liquid ammonia is considered as mixed conductor. Is considered as mixed conductor. How it acts as a mixed conductor? Water. Sodium in liquid ammonia. Consider liquid ammonia in a beaker. This is ammonia. NH3. All these are ammonia molecules. Solvent. Ammonia solvent. Drop sodium metal. Sodium or potassium, lithium, sodium, potassium, rubidium, cesium. If I say only one example in exam, lithium, if lithium comes, then you will get confusion. Alkali metal in liquid ammonia is considered as mixed conductor. See, when we drop lithium metal or sodium metal, any potassium, what happens? Free electrons released into the liquid ammonia. Sodium positive and electron. This is mechanism. Okay, when you put any metal, alkali metal in liquid ammonia, immediately alkali metal release electrons. Now these electrons are surrounded by ammonia, solvent molecules. Ammoniated electrons called as ammoniated electrons. Electrons surrounded by ammonia solvent called as ammoniated electrons. Clear? Right. And this area, sodium ions are present or not? Once observe these boxes. This box and the red box, red color. Answer to my question. In red box, what are present? Free electron ions. In red box. Electrons, ammoniated electrons are present. In yellow box, sodium ion is present. Now you tell me, what is metallic conductor? Metallic conductance is due to what? Free electrons are present or not? Electrolytic conductance is due to free ions are present or not? Over. Metallic conductor as well as electrolytic conductor. Clear? So sodium in liquid ammonia, lithium in liquid ammonia considered as a mixed conductor. Which of the following is a mixed conductor? Sodium in liquid ammonia, model question. Okay, free electrons are present and free ions also present. Conductance due to free electrons is called as electronic conductance or metallic conductance. Conductance due to free ions. Electrolytic conductance. Two types of conductance is present in a solution, single solution. So it is called a mixed conductance. Right? Factors affecting conductance. Ketura, Pragnica. Unnara meer Ketura, Pragnica. Pragnica leva. Factors affecting conductance. See, conductance depends on what? Let us discuss one by one. Size of ion, no doubt one question will come. Not for you, okay? For weekend only, because questions won't come from the starting areas, right? This is just a basic type on. Second part, redox reactions, EMF, questions will come for final NEET. Yeah, this is a basic idea, starting part. Size of the ion. Conductance depends on the size of the ion. Basically, if number of ions are more, conductance is more. If more is the number of ions, more will be the conductance. That is the general idea. Clear? If more ions are present in a solution, conductance is more. Okay. Another important factor, here only we will do mistakes. Clear? Size of the ion. See, if one ion is in smaller size, this is small size ion, large size ion, which will move fastly. Small ion moves fastly, bigger ion moves slowly. Fat person, thin person. Fat person cannot move fastly, correct? Thin person moves fastly, right? If ion is smaller, its movement is more, its mobility is more. If its mobility is more, its conducting capacity is more. See, this is electron. It is lifting electron and it is carrying electron. This one also. Electron means current. Now, on ion A, smaller ion A, some current is present on its head. It can move fastly, sharply. Yeah. But this bigger ion cannot move fastly. So its current carrying capacity is less. Simple relation. If size of the ion is less, its conducting power is more. Smaller ions, mobility is more, moment is more, current carrying capacity is more than bigger ion. Clear? So write the relation, size of the ion. Conductance is inversely proportional to size of the ion. After that, you write this example. Having more conductance, small size. Right. Compare the conductivities of cations of first A group. First A group cations in polar solvents and in non-polar solvents. Conductance of cations of 1A in polar solvent and in non-polar solvent. You have questions in the material. In polar solvent, what are the examples of polar solvents? Polar solvents, water, alcohol, all these are polar solvents. Non-polar solvents, benzene, CCl4, carbon disulfide, these are non-polar solvents. So their conductivity of first group cations is different in polar and non-polar cases. In polar cases, in polar, first I will give the relation, then we will go with reason also. In non-polar solvent, polar solvent and non-polar solvent. See all of you, lithium, sodium, potassium, rubidium, cesium. Lithium, sodium, potassium, rubidium and cesium. In polar solvents, lithium cation conducting power is less than sodium cation. In polar solvents. In non-polar solvents, again we can frame another relation. Given general relation before that. What is the general relation between size and conductance? Conductance is inversely proportional to size or directly proportional to size? Inversely proportional to size. That is general relation. But for alkali metal cations or their salts, conductance of cations of first A, or we can consider salts of first A also. Here you can write salts. No need to discuss separately. Salts of 1A group elements. Salts of 1A elements. Same concept for both. For example, lithium chloride, sodium chloride, potassium chloride, rubidium chloride, cesium chloride. Here also I can take salts. Salts are ions. Clear? So without getting any confusion, you can frame one relation. You can write one relation. You tell me what is the relation in case of polar. One condition is given, that is general condition. Again we can write another condition. Conductance is proportional to, tell me, whose size is more? Size of cation. When you observe the condition, arrange the following salt solutions in the increase. Salt solution means you are dissolving salt in water. Salt solution, aqueous salt solution means comes under polar only, na? In that case, remember this relation. Conductance is two types, two categories, in polar and in non-polar. In polar, or when you observe the word, arrange the following cations, conductance in their aqueous solutions, aqueous water. Then remember this relation. Conductance is directly proportional to size. Whose size is more? So when we follow this relation, when we observe the word aqueous, if you do not observe the word aqueous, non-polar solvents, then conductance is inversely proportional to size. That general relation is there at the beginning. I given general relation. Clear? Right, now you tell me. In case of polar solvents, what is the relation? Online students, in case of polar solvents, if you observe aqueous solutions, conductance is directly proportional to size of the cation. In case of non-polar, conductance is inversely proportional. General relation is given, and one special subtopic, conductance of alkali metal cations are their salts. Here, online students, are you getting? Hello? In polar solvents or in aqueous solution, conductance is directly proportional to size of the cation. In polar solvents or in aqueous solutions, conductance is directly proportional to size of the cation. In non-polar solvents, conductance is inversely proportional to size. Very easy. Let us do one question. Let us start the question. Before that, first year group elements. What are second year group elements listed? Beryllium, magnesium, calcium, strontium, barium. For that also you can apply. Same concept, alkali metals and alkaline earth metals. Clear? To this question, all of you. See model question. Which of the following has highest conductance in aqueous solution? In aqueous solution. Aqueous solution. Online students, what is the answer? Online students. First option. B or A? B. Lithium, sodium, potassium, rubidium, cesium. Cesium size is more. If size is more, conductance is more, because condition is mentioned, aqueous. Arrange the following salts in the increasing order of their conductance in the aqueous solutions. Arrange these salts in the increasing order. Increasing, see, very intelligent people are there. Increasing means they will take a reverse symbol. Increasing means which symbol will come? Less than symbol or greater than symbol? Less than symbol. Which is having low conductivity. NaCl is less than, KCl is less than, RbCl and CsCl. This is increasing order. This is also important. Arrange the following alkali metal salts in the increasing order of their conductivity in aqueous solutions or in their solutions. This is the order, increasing order. Decreasing means this only, na? CsCl is less than. Correct, na? అక్కడ కన్ఫ్యూజ్ అవుతారు. గ్రేటర్ దాన్, CsCl is greater than, డిక్రీజింగ్ ఆర్డర్. ఇంకా మనం నీట్ ఎగ్జామ్ రాస్తున్నా ఇంక్రీజింగ్ గ్రేటర్ కాడనే ఉన్నాం, డిక్రీజింగ్ దగ్గరే. వైష్ణవ్ ఫాలో అవుతున్నాం కొంచెం, నువ్వు మరి అర్థమయ్యేటట్లు పెడితే నీ కూడా. నెక్స్ట్ క్వశ్చన్. Which of the following has low electrical conductivity? In CCl4, lithium chloride, sodium chloride, potassium chloride and rubidium chloride. CCl4, carbon tetrachloride. This is non-polar. In non-polar, conductance is inversely proportional to size. Low means if size is less, conductivity is more. If size is more, conductivity is less. RbCl. Because non-polar is given reverse concept. CCl4 or CS2 or benzene, all these are non-polar solvents. Similarly for alkali metal salts also, MgCl2, CaCl2. MgCl2 and Na plus, whose size is more? Mg plus to Na plus. Compare the sizes, first, second.
Mg plus to
Na plus. Whose size is more? Na. Left to right, size decreases in the periodic table. First year group element size is more than second year group elements. Next, conductance depends on the size. Clear? And temperature also. In case of electrolytic conductance, as we increase the temperature, conductance increases. Next, types of conductance. Specific conductance. Any idea? Specific conductance. Molar conductance. Equivalent conductance. ఏమి గుర్తులేదా మీకు? There are three types of conductances, okay? Specific conductance, molar conductance and equivalent conductance. First keep heading. Specific conductance. Specific conductance. Graphs are very important in this. Specific conductance. Surabhi, follow tunara? Aisha, are you following? Aisha, Surabhi, are you there? Surajin, ఏమైనా ఐడియా ఉందా? మీరెవరు ఏమీ లేదు స్టార్టింగ్లో. In this solution, many ions are present. So many cations and so many anions are present in this entire solution. But let us take one particular area. For example, take 1 centimeter cube area. Specific area. You are selecting specific area. For example, in this room, so many students are there, right? I am selecting students in this area only. These 2 students. Like that, okay? The conducting power of ions present in 1 centimeter cube area of electrolytic solution is called as specific conductance. In specific area, 1 centimeter cube area, how many ions are present? The conducting power of that ions is called as specific conductance. It is the conducting power of ions present in 1 centimeter cube area, specific area. Are you getting? See, in this total room, how many students are present? మీకు అర్థమైనట్టుంది. ఎంతమంది ఉన్నారు? 7 members ఉన్నారు. ఓన్లీ ఈ ఏరియాలో ఎంతమంది ఇక్కడ వరకు 2 students ఉన్నారు కదా. అట్లా క్యాలిక్యులేట్ చేసుకో. డోంట్ టేక్ టోటల్ వాల్యూమ్ ఆఫ్ ద రూమ్, పర్టికులర్ ఏరియా. So in this particular area, how many ions are present? The conducting power of that ions is called as specific conductance. Okay, right. Definition is okay. Conducting power of ions present in 1 centimeter cube area of electrolytic solution. Next, what happens to specific conductance upon dilution? Effect of dilution. See this. Addition of water, very very important. Specific conductance symbol is K. Generally it is called kappa, but let us consider it as K. Kappa. KAPPA. PPA. But we will say K. Let us add water. Dilute this. Addition of solvent or upon dilution. Addition of water means dilution only, na? What happens to specific conductance upon addition of water or upon dilution? Upon dilution. Guess, increases or decreases? See, after addition of water, this is the diagram. Online students. After adding water, you tell me how many ions are present in that 1 centimeter cube area. Same ions are present. After adding water, this is the diagram. In this 1 centimeter cube area, is there any ion? What happened to that ion? What happened to that ion? Washed away by solvent molecules, right? You are adding water. Okay. Water molecules push this Na plus and Cl minus. Clear? These ions are washed out by solvent. Now, how many ions are present in this particular area? 0. So, what happens to specific conductance? Decreases. Specific conductance decreases upon addition of water or upon dilution. Upon dilution. Whose conductance decreases upon dilution? Tell me. Specific conductance decreases upon dilution. The one and only one conductance decreases upon dilution is called specific conductance. Upon adding water, specific conductance decreases. Any doubt in this? Online students, are you following? Surabhi, can you answer? Can you answer, Surabhi? Why specific conductance decreases upon dilution? Why specific conductance decreases upon dilution? Aisha, can you? First, yes. Obed, can you? Can you answer? Obed? Aisha? Bhakti?
Ions get washed away by water molecules, hence the number of ions before and after change decreases.
Yes. Concentration of the ions decreases in that particular area. So specific conductance decreases. K value decreases. Molar conductance. Lambda subscriptum, small lambda, capital lambda, m, mu. See the symbols. Molar conductance. Molar conductance. What we take? Pure water, deionized water. Deionized water. Deionized water means number of ions are 0. Number ions are 0, right? Deionized. Not pure, we can add something, some non-electrolyte also. But ions are 0. Deionized means ions are 0. What is its conductivity? 0. Deionized water, ions are not present, so conductance is 0. Now, Vasavi, again tell me. We are adding 0.5 mole NaCl to water. 0.5 mole of sodium chloride salt. Then conductance of this water increases or not? First we took deionized water and we added a 0.5 mole NaCl, and in other case we added 1 mole NaCl. 1 mole NaCl. In these two cases, conductivity is present or not? Conductance is present or not? In this case, no conductance because this is deionized water. Deionized water. How many moles of electrolyte you added here? 0.5. Here, 1 mole. This solution also having conductance. This solution also having conductance, but which conductance is called as molar conductance? Molar conductance. Conductance by this solution is called as molar solution. Why it is called as molar solution? Because how many moles of electrolyte we added? 1 mole. The conducting power of 1 mole electrolyte present in a solution is called as molar conductance. Molar, 1 mole electrolyte. In this, electrolyte concentration is 0. Here electrolyte is 0.5 mole. Here electrolyte is 1 mole. The conducting power of 1 mole of electrolyte is called as molar conductance. Molar conductance symbol is lambda subscriptum, small capital lambda, small lambda, mu. Molar conductance. Upon dilution, what happens to specific conductance in the previous case? Decreases, but molar conductance increases. Upon dilution, upon addition of water, you see, you are not considering particular area, right? You are considering total solution. What happens when we add water? When we add water, see, once all of you, before dilution, this is one particle, this is another particle, all these are particles, are ions, clear? And this is the volume. See, before addition of water, less area is present, less water is present, volume is less, so movement also less, free movement is less. When you add water, you are adding more water to it. What happens to volume level? Volume level increase. Then between ion to ion, distance increases, free space increases, so movement also increases or not? Only one conductance decreases, that is specific conductance. Remaining all conductances increases upon dilution. Molar conductance increases upon dilution, but specific conductance decreases upon dilution. What is molar conductance? It is the conducting power of 1 mole of electrolyte present in a solution. Molar conductance and temperature effect is given, formulas and units we will see. Okay, definition is okay, everybody? Next, equivalent conductance. Equivalent conductance. Lambda C. Sorry, lambda equivalent. Or we can take this also. Definition. Same. This is deionized water. We are adding 1 gram equivalent of NaCl. Instead of 1 mole, we are adding 1 gram equivalent. 1 gram equivalent. The conducting power of 1 gram equivalent of an electrolyte. 1 gram equivalent of NaCl, 1 gram equivalent of KCl. It is the conducting power of 1 gram equivalent of an electrolyte present in a solution. Conducting power of 1 gram equivalent of an electrolyte present in a solution is called as equivalent conductance, lambda equivalent, or simply lambda, right? What happens to equivalent conductance upon dilution? Same concept. Upon dilution, free space increases, movement for the ions increases, area for the free movement increases. When we add water, what happens? Volume increases or not? Then area for the free movement increases, space for the free movement increases, so conductance increases. Except specific conductance, remaining conductances increases upon dilution. The only one conductance decreases upon dilution is specific conductance. Clear? Remaining conductances increases, right? Once look at this all of you. Equivalent conductance or molar conductance. Molar conductance graph, very very important. To understand this graph, we should write the formulas. First, molar conductance is equal to specific conductance into 1000 by molarity. Equivalent conductance is equal to specific conductance into 1000 by normality. 1000 by normality. By using this formula, by seeing this, tell me what is the relation between mu and molarity and lambda and normality. Direct or inverse relation? See this? Inverse relation. Inverse relation. Mu, molar conductance is inversely proportional to molarity. Equivalent conductance is inversely proportional to normality. This is the formula. Based on this formula we can write like this. Based on this formula we can derive the relation. Can we write like this? Once look at this. Mu is inversely proportional to m. What is m? What is m? What is m? Molarity. What is n? Normality. What are these molarity normalities? Concentration terms. Concentration terms. So can we write like this? Mu is inversely proportional to concentration. Mu is inversely proportional to concentration. Lambda is inversely proportional to concentration. We have Debye-Kukel-Hansager equation. Based on that equation we can derive one relation like this. Hansager equation. Root C. What is C? Concentration. 0 concentration, 2 molar, 4 molar, 6 molar, 10 molar, 12 and so on. Conductance 1, 2, 3, 4, 5, 6 and so on. And now you tell me based on that formula. So online students, what is the relation between molar conductance and concentration? Inversely. If concentration increases, what happens to conductance? Decreases. Online students, correct only, no? Based on that formula, if you increase concentration, what happens to conductance? Decreases. All of you remember this formula. Molar conductance is equal to specific conductance into 1000 by molarity. Equivalent conductance is equal to specific conductance K into 1000 by normality. From this formula we are deriving this, and from this formula we are deriving this. Clear? And based on this relation, molar conductance is inversely proportional to concentration. Equivalent conductance is inversely proportional to concentration. Once look at this. If you go towards right, then concentration increases or decreases? See, concentration increases. If you go in this direction, concentration decreases. Online students, are you following? Online students. First year students, Aisha, first years. Bhakti ikkade undi. Inka Obed. Did you get this? Molar conductance is inversely proportional to concentration. Equivalent conductance is inversely proportional to concentration. So this is a very important graph. Can I draw like this? We are going in this direction, right? In this direction means concentration increasing or decreasing? Concentration decreasing. When concentration decreases, then what happens to conductance? Increases. And see, you are going in this direction. When you go in this direction, conductance increases because inverse relation. If you go like this, means concentration is increasing. You are going like this means concentration is increasing or not? Then conductance value is dropping. No, conductance is increasing because you are coming this direction, right? 12 to 20, you are coming like this. At this point means at 12 concentration, 12 molar concentration, what is the conductance? Tell me. What is the conductance? 1. If concentration is 12 molar, conductance is 1. come towards lower values. At concentration is 2 molar. Then conductance is 5. Okay, so remember this straight line and one curved line. Now the important part, straight line is related to which type of electrolyte and curved line is related to which type of electrolyte. Again, any idea? Online students, Surabhi? Any idea, Surabhi? Straight line related to strong electrolytes. I will give you list of strong electrolytes, and this curved line related to weak electrolytes. The following graph represents dash. Strong electrolytes according to ionic equilibrium. First year ionic equilibrium. Strong electrolytes, strong acids, strong bases, salts are considered as strong electrolytes. Strong acids, strong bases, and salts are considered as strong electrolytes. Strong acids, strong bases, and salts. Example of strong acid: HCl, H2SO4. These are important. HNO3, HClO4, perchloric acid, NaOH, KOH, strong bases, and salts: NaCl, KCl, BaCl2, MgCl2. So you tell me, this straight line is representing HCl, straight line is representing NaOH, straight line is representing NaCl, KCl. So what is the type of graph? Straight line or curved line? For strong electrolytes, straight line. For weak electrolytes, curved line. ప్రాజ్ఞిక ఉన్నారా మీరు? ప్రాజ్ఞిక, కేతురా, ఫాలో అవుతున్నారా? ప్రాజ్ఞిక, కేతురా. Weak electrolytes. Weak electrolytes, weak acids, weak bases. Weak acid and weak bases. Examples of weak acid according to ionic equilibrium. Srujan, tell me weak acids list. Acetic acid. Acetic acid. Next, another weak acid, H3PO4. H3PO4, weak acid. HCN is weak acid. Hydrogen cyanide is weak acid. Next, H3CO2, carbonic acid. H2CO3. HNO2, nitrous acid. Based on first year ionic equilibrium. Weak bases, weak base category. Very important weak base. आयनिक इक्विलिब्रियम में आइडिया नहीं आपको? अमोनियम हाइड्रोक्साइड, aluminum hydroxide, zinc hydroxide, all these are weak bases, but important ammonium hydroxide. Next, formulas related to cell constant and units of specific conductance, all types of conductance. Conductance is equal to 1 by R, reciprocal of resistance. Conductance is reciprocal of resistance. This is electrolytic cell. Electrolytic cell. Positive, negative. What is positively charged electrode? Positively charged electrode. Anode. Negatively charged electrode is cathode. Let us consider the distance between two electrodes. Electrolytic cell. In electrolytic cell, which energy converted into which energy? Chemical energy, electrical energy. Electrical energy converted into chemical energy. Electrolytic cell is a device in which electrical energy converted to chemical energy. It is having two metal rods. One is cathode, one is anode. Based on the science, we will decide which is cathode and which is anode. Okay. L is the length between electrodes. Length between electrodes. Resistance and length relation, and resistance and area of cross section. Area of the cross section. Width of the rod, electrode. Area of cross section of the electrode. Conductance is equal to 1 by R, or inversely proportional to resistance. And see, resistance is directly proportional to length between the electrodes. If length between the electrodes is more, means if electrodes are separated by a large distance, conductivity of the total cell is less. Sorry, resistance is more, conductivity is lesser. What I am saying, if length between the electrodes is more, then resistance is more. If resistance is more, then conductivity is less. First, resistance and length relation. R is directly proportional to length, and R resistance is inversely proportional to area of cross section. Area of cross section. Combine these two. Combine these two. R is proportional to L by A. Remove proportionality. R is equal to rho into L by A. Rho into L by A. Right. Next, take 1 by R. 1 by R. Or do one thing, send that side, after that take reciprocal. Send L by A this side. Send L by A this side. Rho is equal to R into, tell me, A by L. Well, just we are sending L by A this side. Rho is equal to R into A by L. Okay. Then take 1 by rho. 1 by rho is equal to 1 by R into L by A. Take reciprocal for this. Reciprocal for this equation. Reverse it. 1 by rho, 1 by R, reverse. L by A. L by. 1 by rho is called as specific conductance. We know about specific conductance definition and dilution effect. K is equal to 1 by R. 1 by R into L by A. This is a very important formula. Specific conductance is equal to 1 by R into L by A. 1 by R into L by A. Specific conductance is equal to 1 by R. 1 by R can be written as C. C into L by A. We can give one notation for L by A, G star. G star. G star is equal to L by A. This is main formula, 1 by R, C into L by A. What is L by A? One special word is there for L by A. Cell constant. L by A is called as cell constant. 1 by A is cell constant. And you tell me, 1 by R is equal to, in place of 1 by R, what we can write? C. At the beginning I given that one, you know. C is equal to 1 by R, remember this also. In place of 1 by R, what we are writing? C. Clear? So say the formula. Specific conductance is equal to 1 by R into L by A. These star marked boxes are very important. These two formulas. Sometimes we have to calculate cell constant L by A. What is L? Length between the, what is L here? Length between electrodes. Length between electrodes. A is area of cross section. Okay. Let us write the units. Units for specific conductance. Units for specific conductance. Units. Specific conductance, molar conductance and equivalent conductance. Specific conductance, a small derivation is there. Okay, we write area units, length units. After that we will get these units. Ohm inverse, centimeter inverse. See, when you get these units, ohm inverse, centimeter inverse, that units are related to specific conductance K units. Ohm inverse is centimeter inverse. For example, 200 is the conductance. You tell me which type of conductance unit value this is. Can you say? Which conductance is 200? Specific, molar, equivalent? No. But you tell me ohm inverse, centimeter. Now this value belongs to specific conductance. So based on the units we can find type of conductance. So specific conductance units are ohm inverse, centimeter inverse. In place of ohm inverse we can take Siemens also. Siemens meter inverse or Siemens centimeter inverse. Ohm inverse can be replaced by Siemens inverse. Okay. And molar conductance units. Ohm inverse, centimeter square, mole inverse. Ohm inverse, centimeter square, mole inverse. Equivalent conductance, ohm inverse, centimeter square, gram equivalent inverse. Ohm inverse, centimeter square, gram equivalent inverse. Ohm inverse, centimeter square, gram equivalent inverse. Okay.